Respected all, good afternoon. A warm welcome to the third session of the day 2 of AICTE sponsored 1 week faculty development program on design thinking for manufacturing excellence, organized by Department of Mechanical Engineering, Faculty of Engineering and Technology, Manav Rachna International Institute of Research and Studies, Faridabad. This session is on integration of advanced analytical tools in design. The eminent speaker for this session is Mr. Sharad Mahour. Mr. Sharad is MTech in tool design and his valued experience includes position as Senior Application Manager at Messrs. Design Tech Systems Private Limited, New Delhi. He is actively involved in industry-supported projects, especially in the field of product design and development. Heartiest welcome to Mr. Sharad Mahour.
Thank you so much, sir. Thank you so much for the nice introduction.
Thank you, sir. Now over to you, sir, please.
Okay, just please allow me to share my screen. Actually, I am unable to share my screen.
Okay, sir. Sir, we are like updating the rights. It's given, sir. You can share now.
Yeah. Please confirm my screen is share or not sharing or not.
Yes, sir. It is shared. Visible,
Okay.
sir.
So, good afternoon, all, and thank you so much, all of you, just for attending the session on the integration of advanced analytical tools in design. So, first of all, we will start from just from the about what is the Altair and the what is the design tech and from where I belongs. Just I will take only your 4 to 5 minutes just for a brief introduction about my company. Then we will move forward towards the design for manufacturing. What is going on the in this modern era for the manufacturing industries. So myself, Sharad Mahour, actually I am an application engineer in the Design Tech System Private Limited and working as a senior application engineer in the New Delhi office. So basically, Altair is the US based company. We have a headquarter in the Troy, Michigan. It established in 1985 and in 1985 Altair put its step into market with the hypermesh. Most of you also aware about the hypermesh, that is the world known best software, or you can say the tool for the meshing or the pre-processing. And from that 1980 to 2021, Altair is a big shot in the market, and it is a around $500 million company. And Altair has the 3,000 plus engineers, scientists, creative thinkers, and its presence almost around the 25 to 30 countries, and more than 11,000 of customer base Altair have. And if I talk about the tools or if I talk about the products, and so it has a very long list about the product. It has more than 150 plus softwares and products available with the APA. APA means Partner Alliance. So here you can see these are basically a big shot I have mentioned on this slide, because there is a very long list of the customer list. So I cannot put every customer logo in this slide. So I have put some slide according to the segments. Here you can see the from every major industry is using the Altair. Some are using for the physics simulation, some are using for the, you can say the HPC, IoTs, AI, data analytics. So So what is the design tech? So design tech basically the national level channel partner with the Altair, and we have more than 20 plus years of experience in the field of the CAD CAM CA domains, and we are the top solution provider for the CAD CAM CAs. And along with the Altair, we have some another, you can say, the business partner associated with us, just like the PTC for the Creo, Stratasys for the 3D printing, engineering services. And if I talk about the design tech is presently uh, has the presence in the 9 cities in the India, along with the overseas, just like the Canada, Germany, Singapore, and Hong Kong. So basically, uh, this shows you the complete overview about the Altair. If I talk about the design and modeling and visualization, means to say, uh, just for doing the pre-processing, meshing, set up the boundary conditions, doing some CAD editing, and visualize the results. All these things you can done with the help of this bunch of tools that comes in under the design modeling and the visualization. If I talk about the physics simulation means to say Altair have the very long list about the solvers, multi-body dynamics, CFD solution, manufacturing solutions, and structure analysis, implicit, explicit, fatigue analysis. But now the Altair also have come into the data analytics, Internet of Things, HPC, and partner alliance as well. So move towards the today's agenda. So just moving down to you to about the what is the advanced integration of the means to say advanced integration of tools in the manufacturing era. If I talk about the 1980s, so in 1980s all the design were done with the help of the some means to say with the help of some drafters, pens, pencils, uh, drawing boards. With the help of the drawing boards, all the designer do the manual or handwritten drawings. After that, that era was spent. Then after that, some 3D modeling tools or 2D modeling tools come into the picture, and after that, some manufacturable drawing has been done with the help of these 3D softwares, just like I think in the very recent now the very long list of available in the CAD tools available in the market. But first software that I remember, I think ideas was there. The most of industry people used to do the drafting and some 3D modeling, parametric modeling. Then after that, CI softwares comes into the picture just to validate the design. Suppose some design engineer had designed the part, and if you have not the facility about the testing the part, then you have to make a single part and fit that part to your assembly and run the assembly just to check whether it will fail or run properly. Suppose it will fail, then it will uh, means to say the it will waste of lot of time and the money. So with the help of the CAE software, designer design the model and send to the CAE software CAE guy just to analyze. If some there is some modification or changes required, then CAE guy send back to model to the designer, and designer do the changes and modification to the model, and again send for the CAE, send for the simulation or send for the analysis. So there is a very means to say a very to and fro motion of the model. So due to which it takes some lot of time to develop a product from scratch to final. And in the 20s, if I talk about the mainly 2010 or 2020, now the most of the uh, tools, or you can say the most of the analytical tools are available in the market, that you can initially simulate or initially analyze your part or model or component at the designing stage itself. You don't need to send your part to the simulation guy. Suppose if you want to do the some a very deep diving into the simulation, then you have to go for the specialist, simulation specialist or analytical guy for the simulate that particular component if it is very critical. But at the designing stage, just to finalize the design, there are lot more tools are available in the market. And so today we will talk about those tools, what are the latest trend is going on at the designing stage, and those at the designing stage, what type of component had been designed, and how can you check that the manufacturability of those components. Those components are feasible or not. If those are feasible, then how can we check with the process, for which process it is feasible. Suppose you have created some very irregular type of component and it is not feasible for the casting, not feasible for the extrusion, then how will you make that? You will make that of the 3D printers, metal 3D printer, then it will take more cost to develop. So today we will talk about this process, as you can see on my screen. So basically, these process comes under the Altair Inspire family. Altair Inspire family, that is the simulation-driven design for manufacturing. What is the simulation-driven design? That I have explained in this slide. So you can do the simulation at the designing stage. So this name simulation-driven design derives from that particular statement. So first of all, as you can see on the extreme left, that is the casting. We will look into the some casting processes. How can we uh, simulate the casting process, and after that the forming, sheet metal forming simulations. So I just tell you the software names as well. Casting simulation is being done with the help of Inspire Cast, just to check the feasibility and the whole process simulation. Inspire form used for the metal forming simulation, for checking the sheet metal component feasibility, nesting, and full process simulation with the help of the die, punch, binders. Binders means blank holders, constraint pins, pad, etc. And Inspire mode for use to check the feasibility and do the process simulation of your injection molded parts. And Inspire Extrude, we have two types of solution available for the Inspire Extrude. One for the extrusion metal and second for the extrusion polymer. And next is the additives. Additives means to say 3D printing simulation. With the help of the 3D printing simulation, you can check the deformation, you can check the uh, thermostatic effects of your component, and what would be your support material and how will you slice the component. All these things you can capture and do with the help of the Altair Inspire. And last but not least, that is the PU forming. That is the new family member added to the manufacturing segment. That name as the Altair Inspire Polyform, used for the forming simulation. Basically, forming simulation. Here also you can check the example. I just I think video is not playing. Just yeah, here also you can check the example of the how form get fill into the your die, that is the shape of your car seat or steering wheels and some other insulation parts that are available in the market. So first of all, moves towards the concept generation. How will you generate the concept? Suppose you are a product designer, and how will you start your means to say the how will you do the scratch to final, means to say how can you go from scratch to the final, what would be your steps, and what type of stages you go through. Suppose first you will do the handwritten drawing, pen paper drawings, and you will directly go to the CAD softwares, 2D softwares or 3D software, or directly go for the some advanced tool just like the CAE tools available in the market that are used as designing stage. So these types of questions comes into the mind once you go for a new product design. So I just show you how these types of tools help us to decide its topology, what would be its volume, what would be its area, what would be its material, and what would be its shape and size, and what would be the suitable manufacturing method to produce that part. So I have taken an example of the landing gear bracket of an aircraft. So I have simulated that, and first you just see the video of this landing gear. Basically, that simulation has been performed into the Altair Inspire. Here you can see the logo and branding of the tool. So landing gear touch the ground, and once it touches the ground, then it faces some motions with its relative part. So we will take one bracket, one this bracket we have taken just to showcase how can we design this bracket or how can we optimize this bracket basically. Yeah. So due to this motion, this tool also will tell me that what type of forces and what type of reaction forces components are getting, how much force a component is bearing during this operation once the landing gear touches to the ground. So here you can I just lay all the videos. Yeah, on the right hand side video you can check the forces, what the forces are coming out from this type of motion, or when the landing gear touches the ground. So these forces and these reaction forces help us to identify the component shape. Suppose if you want to design a bracket for something, if you want to design a shaft for something, then first of all you should know about the what type of load it would bear during the assembly. If you know that, then topology optimization will help you a lot. So basically, what is the topology optimization? So topology optimization, this is the you can say the relation between the material density and strain energy of your uh, component. So in the topology optimization, according to your boundary condition means to say suppose you have fixed your component from one hand and apply a load on another hand, and the load could be any kind of load you can apply. Thermal loading, it would be some torque, it would be some linear monotonic loading, it would be some any uh, dynamic loading, frequency response or transient type of loading. So if you know about the tentative loading of that particular region that should come onto the component, once you apply those type of loading on any type of design, then software will suggest you the perfect topology, perfect shape. Basically, suppose you have designed a shaft of 100 diameter, but you are applying a load on it about 10 kilonewton, and your shaft diameter is the 100 diameter. Then once you uh, bring your tentative design of your shaft with 100 diameter to the software and apply the load and the boundary condition, then software will suggest you have selected a very lot more material to your component. Basically, with 100 kilonewton, for the 100 kilonewton, this a very big diameter is not required. So software will automatically scoop out the material from your shaft and suggest you some optimized designs. So now the time you can take the real life example of that. You already know about the bike in the market that is a very popular, that is KTM. So KTM have the ribs on the uh, around the engine mount. So basically these ribs ideas come from the topology optimization. If you take the example of any previous bikes and in the that runs into 2010, 2015, so there will be uh, there used to a very thick material over there, but in the uh, new launched bike you can see the some ribs are there. So basically those ribs are the optimized design. So optimized design means to say what type of loading component is getting. So to bear that load, those ribs are sufficient. You don't need to put the whole plate over there. So that is the topology optimization. So in this first section, uh, we have covered the means to say what type of loading we are getting. If you know about the loading, that is very good. If you don't know about the loading, then we have to do for the some kind of iterations. So move forward. Here you can check, this one is the base design. Base design means to say I just want to make a bracket for this, and I have just designed a very simple bracket, just a kind of a box type of bracket I have designed. I have no idea what type of ribs it should have and what type of some strengthening feature it should have, but I just directly uh, put a box type bracket over there. And once I do the motion analysis, if you know about the loading, you can also directly put the loading on that, and software automatically, tool automatically suggest me the shape of my bracket according to the boundary condition and according to my symmetry planes, what symmetry planes I have defined. So what is the importance of the symmetry plane? If I will not apply the symmetry plane for the topology optimization, then software will do by itself. Once it's do by itself, then it may not be for the manufacturable. How can you you have designed the component but it is not manufacturable, then that is no point of that design. So here you can check with the iteration, doing the iteration, here the concept 1 and this one is the concept 2. So basically these are the fundamentals of the concept generation. Most of the industries are using these types of tool for getting the initial designs. They get the initial design according to loading, and after that they fine tune these types of design, just to add ribs, just to add some material removal holes, and added the material, modify some other topology feature of your component. So initial design, if you want to get, then these types of tools are very beneficial at the designing stage, just to get the concept, what type of my component should be. And we have got the component, then now let's check its manufacturability. How can we take it for the manufacturing? So here I have explained, I have put a workflow. Workflow means to say, if you don't know about the loadings, then you have to do for some kind of motion analysis, just to extract the loads, how, just to identify how much load your component is getting. If you know directly, then apply the directly. So with the help of the Inspire, we have done the topology optimization. Topology optimization means to say, get the initial design. If you if you are not sure about that uh, software given design, then that optimized part you can also analyze with any software, you can do with any tool you can do. So if you cross check that optimized part, then we directly go for the in which I have applied only for the 3D printing, because this type of bracket, I think it it would take very it would take very cost for the manufacturing if I take it to the casting process. But no problem, I have take it for the 3D printing, because I have to just to show you what the 3D printing simulation. So optimized bracket, going for the 3D printing simulation. In the 3D printing simulation, you can also uh, check its manufacturability with the help of the metal 3D printer. In the metal 3D printer, you can orient your component accordingly. Once you orient your component, then it will suggest you the what type of support it should have, and what type of material you want to take for the support structure. And once the component it starts to printed, what would be your slice thickness, and once the component get ready after the printing process, then what would be the deflection, structural deflection. So these types of manufacturability you can check of your concept design. So move towards the next manufacturability of the another bracket. In that in the previous example, I have taken the uh, same kind of bracket, but that was into a aircraft. Hello, I think there was some disturbance. Uh, disturbance, no problem. So previously I have taken an example of the bracket that was I have put into a aircraft landing gear, but same type of bracket I have put along with a small assembly. So on the right hand side you can see, not the right hand side, I think it is showing the whole process. So after the optimizing, it has given an output just kind of this type of topology optimized product. But now the time I don't want to check with the 3D printing, I want to check with the help of the casting simulation. So with the help of the Inspire, you can directly simulate the component as the get the output about the what would be your shrinkage and where it would be, shrinkage porosity where should be. So because for getting the shrinkage, if I talk about the casting process, so for getting the shrinkage, your component thick from where your component thickness is very high, so it will take more time to get solidified from that particular location. Okay, so if that thick region solidified in last, then there would be some tendency to get shrinkage porosity. So it is also showing the shrinkage porosity tendency. Basically it is the feasibility check after the optimizing. So all these types of process, you can easily do with the help of the Altair Inspire. I have taken the example of the casting, but if you are doing with the if you are doing the optimization of your sheet metal component, or suppose if you want to give the strength of your sheets, so these type of optimization you can do just to play with the thickness of your sheet, and software suggests you some bead location where the bead location should be, and just to give the strength. Suppose if you have a 2 of thickness, then you want to optimize that 2 of thickness part is getting deformed under a particular loading condition, then you want to optimize that particular part, but you do not increase the thickness of your component, because uh, if you increase the thickness, then it may affect your product efficiency. So if you optimize these type of sheet metal part, then software suggests you to the provide the bead pattern. So once you apply the bead pattern to your component, then your component get more stiffer, it gets some more stiffness than the plain one, or you can see the previous one. So that was about the concept design, concept generation. Once you get the concept, then how can you check the feasibility of that? How can you check the manufacturing feasibility of that? How, if you are generating a concept, then it should be a manufacturable. So moving towards the next manufacturability check tool, that is the Altair Inspire Cast, used for the casting process simulation. So basically, what is the Inspire Cast? It is a, you can say, the very fast technology it is, because user don't need to mesh the component manually, software do the automatically. You can play with the mesh, but in very limited region. It is very easy to use, only 5 commands are there, because uh, these tools will be used at the designing level. So it gives you very accurate results. And more important thing about the casting flow simulation tool, that is the it works on the biphasic CFD formulation. So what is the meaning of the biphasic CFD formulation? It gives you the result of the filling simultaneously as solidification. It gives you both results simultaneously, filling and the solidification. But if you want to check the filling only, then you can go for that. If you want to check the solidification of your component only, just to predict the porosity, or just to check the shrinkage porosity, you can go for only for the solidification. But if you want a full package, means you say filling and the solidification, then you can do these both type of an analysis simultaneously. So okay, start one by one. So with the help of the casting tool, casting feasibility tool, just to check the manufacturability of your casting component, your component is feasible for the casting process or not. So there are various types of operations are being used in the industry for the casted products. So start from the one. First process is the gravity sand casting. In the gravity sand casting, your mold made up with the help of the sands and molten metal pour into that particular mold, as you can see in the picture. And next is the gravity die casting. Your mold or your die are made up with the help of a metal, and molten metal pour into the cavity with the help of gravity only. No external force needed for this process to inject the molten metal into the cavity. And next is the gravity sand is the same. Yeah, that is the investment casting, in which a wax pattern are made, and those wax pattern are poured into a slurry, and uh, repeat this process just to make a thick wall around the pattern. And after once the pattern get sufficient thicker just to bear the molten metal heat, then pattern are made up of the wax. Once you pour the molten metal into the pattern, then all the wax melt out, and your molten metal gets settled into the slurry cavity. So basically this process is used for the casting of very precise components only. And last two processes are the low pressure die casting and the high pressure die casting. Basically, what is the difference between the low pressure die casting and the high pressure die casting is the in the low pressure die casting, as name suggests that, mm, in the low pressure die casting, your injected pressure is low, but in the high pressure die casting, your injection pressure is very high, just to inject the molten metal even into the very thin ribs. So low pressure die casting are usually made up for casting of the aluminum wheels and alloy wheels of your four-wheeler and two-wheelers. But high pressure die casting are used for making the cylinder heads, engine cover, all these type critical component in which have the very thin wall sections are available. So these type of component produced with the help of the high pressure die casting. In the high pressure die casting, very close tolerance can be achieved. So with the inspire cast, for checking the casting feasibility, you can check all the templates that you are that you can see on my screen. You can check the feasibility for the gravity sand, you can check the feasibility for the gravity die, low pressure die casting, high pressure die casting, tilt pouring, and even for the investment casting. So what are the main capabilities we have just to design the component, or just to analyze the component? So first of all, with the help of these tools, you can create and modify your geometry in this tool itself. You don't need to switch between the uh, Inspire product, Altair Inspire product, and CAD software. You don't need to switch between in these two. Suppose if you want to create a surface, if you want to create a solid, if you want to create some uh, overflow, then you don't need to go for the CAD software. You can do in itself. So on a single click, you can create the riser. Suppose you are doing a iteration for the casting feasibility check. Suppose you think that a riser should be there because component is not filling properly. If component is filling properly, but there is some air get entrapped at some particular location, you want to put the riser of that, then on a single click you can put the riser. If you are same doing in the template of the high pressure die casting and same air get entrapped into some region, then with the help of a single click you can apply the chiller, you can apply the uh, overflows. You can easily create the mold in that. Suppose you have import a complete shot of your casting. Complete shot means including the feeding system as well, gate, runner, overflow, riser. So that known as the complete shot. If you have imported a complete shot for the feasibility check, that you have created your complete shot, okay or not. So so if you want to do some modification in that, then these type of geometry related modification can be done very easily. And why we need to do these type of analysis at the designing stage? Suppose you have created a complete shot, then according to that particular shot, your die would be manufacturable, your die would be fabricated. Okay. Suppose with your experience you have created a complete shot or complete model of the casting and sent it to the tool room guy just for fabricate the die. Once you send the complete model to the tool room guy just to fabricate the die, then it will put a block of steel and put a block of steel into the CNC machine or the VMC machine just to cut the material. Okay, but you don't know how the material, molten material, will behave according to your cut cavity. So before going to the fabrication, we have to check first at least our design. My design is working properly or not. Suppose you have created the die, but your component is not filling properly. It is getting the non-filling. Half portion is filling and half portion is not filling. Then what would we do? Because lot more time and money have already wasted. So we have just at least we have to check these designs at the designing stage. So I have already told you only 5 commands are there just to simulate the casting. Just to simulate the casting, only 5 commands would be there. First, just to designate the component means to say designate the part. Designate part means tell the software this is my finished component. Others are the geometry region, or you can see other are the other members, just like the overflow, riser, chiller, or cooling channels. And after that, define the gate. What would be your metal entrance region? And after that, create or import component. If you have already created some components, means to say other component, riser, chiller, etc. If you have already done that, then you can directly import those. But if you have not, then you can easily create in. Then set up the process, means to say what type of setup you want to simulate: HPDC, LPDC, tilt pouring, GDC, die casting, gravity casting, sand casting. So select, set up these process and run the analysis. Once you run the analysis, then it will show you the results of your filling and simulation. In next session, I will give you a demonstration of that, how we set up the process, and how we can get the results, and what the result tells us, what is the problem the design has, and what we need to modification. So that all about the casting process. And if I talk about the complete manufacturability, then we need to cover also the forming simulation as well. So Altair Inspire form is used for the forming simulation, sheet metal forming simulation. So if I talk about the sheet metal forming simulation, if I talk about this sheet metal forming simulation, so three things comes into the mind. Suppose you get the finished component from, for example, you get the finished component from the Maruti, okay, and finished component design from the Maruti, and you got the order about that, and you need to design the die and fabricate the die and produce the component and finish part sent to your customer. Suppose, take an example. So first of all, you should know about the feasibility. Suppose Maruti have sent me the finished product, Maruti have sent me the finished product, then I should know about this feasibility. It is feasible to manufacturable by the press tool or not. So just to check the feasibility, uh, we go for the feasibility check, or you can say the one step check. One step check. In the feasibility, you can directly open your complete blank, complete blank, and once you open that complete blank, you can also get the tentative results about the thinning. What would be the thinning of your component, what would be spring back of your component, what would be the FLD, forming limit diagram, from where your component is in a very good region, or from where your component is the marginal region of, from where your component is getting fractured. These are the tentative results. Software tool, analytical tool give you once you do the feasibility check, okay, and also give you as output as the open blank shape. So from open blank shape, you get the idea how much sheet will be utilized to produce this component, this part. So once you're done with the open blank shape, then take it for the nesting, nesting or the fit accesses. So
क्या है?
take it for the fit analysis. In the fit analysis, your open blank shape is fit into some particular shape. Particular shape means your open shape will be fit into a rectangle, trapezoidal, irregular trapezoidal, chevron, these type of shapes. So after putting this shape, software will give you the percentage utilization, how much uh, material is being utilized, how much material is being utilized from your sheet, and how much material is being wasted. So these type, basically these nesting comes under the part of costing. So once you get the weight of your utilized part and the waste part, then you can easily calculate the waste money and utilized money. So capability of the inspire from that in this tool as well. You don't need to do the mesh your component, because software will do in background process. All the materials are available in the inbuilt material library as per the US, Japanese, and European standard. Uh, you will get the most of the processes are the automatic, just like the stamping orientation means to say in which direction your component is being stamped, and you can easily apply the blank holding force and draw beads. As I told you earlier, once you're done with the feasibility analysis, then you can visualize the results of the thinning and FLD, and after that you can take your open blank shape to the blank fit and nesting. So here I have show you a feasibility workflow, yeah, how we can simulate the feasibility analysis. Just first of all, import the model. If your model is the solid, means to say the it has some thickness, then you can easily extract the mid surface. Defeature all the feature means to say if you have some holes, cutouts, and bands, then you can easily remove those with the help of just single command. Add the material. There are lot many materials are available. As you know, all you know about the market is moving towards the EVs and the high tensile of the material. So all these types of high tensile of material are also available. Process setup means to say in which direction you want to stamp your component, in which direction you want to form your component or stamp your component. Add constraints. Suppose if you want to apply the blank holding force or constraint ring, then you can easily apply it, and after that run the results. So once you're done with the run, then you will get the results just like this. Basically these are the results of the thinning. So here you can check the it is getting the 19.5% of maximum thinning. It is getting around the this whole region. It the thinning result comes during the feasibility test. And on the right hand side here you can check the blank nesting report. It will give you a whole report about the what type of cutting force required, what type of shearing force required, and what is your blank parameter. All these things you can get into the blank nesting report. So once you're done with the feasibility check, next process comes that the tryout. Tryout you can say, or you can say the incremental. In this incremental or tryout, previously you have not used any die, punch, blank holder. You have not used these tool members. You have just used only a finished component and open that component. But in the tryout process, you properly simulate your sheet with the help of the die and punch. how the punch is coming, and when the punch start form your sheet, then what would be your sheet metal behavior, how the material get flowing during the forming operation, first forming, how the material is behaving in the first forming, how the material is behaving in the second forming, what the conversion in the thickness. In the first forming, the sheet thickness was 2 mm. In the second stage of forming, it remains as the 1.5, and the third it remains as the only 1 mm of thickness. So these types of analysis you can do, and also check the tool forces that are very important factor that plays a role in the press tool industry, or you can say the sheet metal industry. So if you know about the loading, how much your die is making load to the component, or how much your punch is making load to the component or sheet metal, then it will help you to predict the uh, press selection. So what press tonnage would be required to form this particular component? So same type of uh, results you can get into the tryout process, but tryout results are the actual results, and it gives you the thinning results, FLD, failure contours, stress results, strain results. And one more important thing about this inspire from that, if you suppose you have only a die face, then software automatically creates its opposite tool member. If you have die, then it will automatically create the punch from the die itself, and automatically create the blank holder from itself. Just you need to give only one die member. So this is the, you can say, the tryout workflow. Just first of all, import the model, select the blank. Select the blank means to say, if you have a single blank or the tailor welded blank. Tailor welded blank means uh, in the manufacturing industry, it is a very popular trend, or you can say the popular trend, but it is a customer demand. Tailor welded blank, in which, suppose uh, you want to form a sheet circular sheet. So half portion of that circular sheet would have material of steel, suppose, and half portion of that circular sheet would have a material of brass, and these two semicircles are welded from its center. So these types of blanks are known as the tailor welded blank. Their thickness also you can vary. Suppose a steel portion have the thickness of the 1 mm, and brass portion or the copper portion has the thickness of 1.2 mm, and welded together. And after the welding, you put your blank into the die for the forming. So that is known as the tailor welded blank. So select the blank, it is a single or the tailor welded. If it is single, then what would be its thickness and its material? Set up the process. What process you want to simulate? You want to simulate the crash form, you want to simulate the single action operation, you want to simulate the multi action, you want to simulate the trimming, you want to simulate the spring back. There are lot many modules are available as per the physical testing, related to the physical testing. Um, because these types of operation are also used into the production houses just to produce the sheet metal product. And once you're done with the running process, then you will get the result just like this. Here you can also check the results of the thinning, and this is the result contour of the FLD. So in the next session, I will give you a overview on this FLD, just to show what color tells us. So what is the meaning of this green region and what is the meaning of this cyan and blue region? And it also helped us to predict the region of the wrinkle, region of the fracture, from the which reason we are getting the wrinkle and which reason we are getting the failures. These are the example of the spring back. If you have done the spring back simulation, then you will get the results of the spring back. Then once you get the results of the spring back, then you can easily go for the die compensation. Die compensation just to prevent the spring back to your component. So in the design process, you just design your model. Okay, you just design your concept. Suppose you have designed a sheet metal component, but you just need to check the its manufacturability, because when you design the model, that is the very ideal design, because it it doesn't have the spring back, it doesn't have the any manufacturing defect, it doesn't have any, means to say, material modification. But once the metal goes to the production, then it gets all the things. It gets the wrinkle, it gets the fractures, it gets the scratches during the forming simulation. So you should consider these things before designing. So I think I have covered three processes, but if you have any question and query till now, then you can please ask in between. And if you have any question, then you can ask, or we can move forward. Hello.
Hello, sir.
Yes, sir.
Sir, how much this software would be cost if I take this for the simulations?
Sir, we can discuss this means to say commercial points in this separately. Basically, I am from the technical background, so if you are interested to see the more details about the alter or the manufacturing processes, manufacturing solution, then we can do a separate session for you, and my commercial team will contact you about the this costing matters.
Okay, sir. Thank you. One more question, sir.
Yes,
Uh,
sir.
so I usually do orthopedic implant designing, that hip implants and the orthopedic implant.
Okay.
So I also need the simulation thing. So we used to prefer ANSYS for the simulations. So is it like feasible for orthopedic implant simulations here also?
Yeah, sure, sir, sure. So, what type of simulation you do with ANSYS?
Okay. And is
Just
this, yes, sir. Is this software is available for MacBook? And
yeah. It is available for the MacBook, Linux, and the Windows. So, when you design, so what type of simulation you do with ANSYS? Linear, static, dynamic analysis, multi-body dynamics. What type of
yes,
analysis?
sir. So I need the dynamic analysis right now.
Okay, but once I complete these manufacturing process, I have one interesting tool that is the meshless technology, and that is very widely used in the field of the medical background, because if you design a bone with the realistic bone, you have designed or you have scanned a realistic bone, then it get more time to do the mesh. But if you do the mesh, then your mesh size would be very fine. Hmm? If your mesh size would be very fine, then it will automatically take you more time to get simulated. So just to remove all these things, we have a meshless technology. So you just apply the boundary condition and run the analysis. No geometry cleanup, no meshing required.
Okay, thank you, sir. Thank you. Looking
Hmm.
forward.
So next manufacturing process we will cover, that is the extrusion process. Extrusion process for the polymer. So extrusion you can do for the metal as well as polymer as well. So start from the polymer. So basically what type of you can say what type of defects you can predict at the early stage. Basically the all these tools are used to predict the manufacturing defects at the early stage, before the die manufacturing or before the production, just to redesign your component and redesign your die structures. So here you can see basically this graphs belong for all the analytical tools, but I have mentioned over there for the Inspire Extrude. So here you can see uh, blue line goes for the traditional approach. Traditional approach we used to do in our past, and most of the industries are using the same now. They are going for the traditional approach. They are wasting their lot of money and lot of time in this trial and errors, die trial and die errors. So because they think they have a lot more experience about these things, so that's another matter. So look into the first stage, that is the die design. Blue line for the traditional approach and red line for the simulation approach. Suppose you have done the simulation at the earlier stage. So I have a tool, the Inspire Extrude. So I have mentioned the name of that, Inspire Extrude for the polymer. So look into the die stage. So in the traditional approach, designer don't need to do more work in this section, die design section, because they have already some previous die and they have experience. So according to the experience, they design the die and design the component and send for the manufacturing. But if you have the simulation, if you have some analytical tool, so you need to design your component again and again, modify your component again and again. Because if you design something and go for the simulation, then it is showing some defect, then you have to add it at that stage only. And here you can see the fabrication cost is very high in the traditional approach, because traditional approach compared to the simulation approach, because in the fabrication stage you can most of the costly thing you can remove with the help of the simulation. Suppose some more moving inserts are there, some cylinders, hydraulic cylinders and moving mechanical slides are moving into the die. So if you want to do the experiment with the help of your simulation software and the CAD software, you want to remove some your moving slides, then you can remove those things. And after removing that, you can simulate the component or simulate your die, just to check I have removed 2 or 3 cylinders, then how my component is behaving into the die. So with this iteration process, you can also remove the fabrication die. But in the die trials, if you have already done all these things in the designing process, then your die trials will go easily. But if you have not done work into the die design, then you have to pay for in the die trials. Because suppose your die goes to the machine at the first trial, then it will show some error, then you have to remove that error, and after that again go for the trial, then again go again get the error, again go for the trial, again get the error. Then these process, uh, for these process you have to spend more money. So just like in the production as well, you have not simulated your die for the number of cycles or the number of products. So your die will get wear and tear, and your component will get more defect after a period of time. But you have, if you have already simulated your component for the number of cycles, then you have also you have also taken the margin for the wear and tear, and your component will not more defect after a long time run of die, and your die will not get wear tear after a number of cycle run. So basically, with the help of the inspire extrude for the extrusion process for the polymers, so what type of defects you can predict at the earlier stage, or you can remove those? So first is the profile distortion. So basically, what is the profile distortion? Uh, I think most of you already know about the extrusion process. So I just tell you again that
அதையும் ப்ரொஜெக்ட்
if
இருக்கா?
you
சரி,
put
நான்
a
என்ன பண்ணுவேன்?
pressure, yeah,
அப்படியே வர மாட்டேன்.
हेलो 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 शरद सर।
hello.
हाँ सर, आपकी आवाज नहीं आ रही।
Actually, oh, I have muted.
या
Yeah. So I was talking about the polymer extrusion process. Now I'm audible, sir.
यस सर, यस सर।
Yeah. So I was talking about the polymer extrusion process. Actually, I have explained all the thing, but I don't know, I was on mute. So sorry for that. So yeah, I was explaining this graph. So basically, if you have done work at the designing stage with the help of the simulation software, then it will take more time in the designing stage. Because in the designing stage, suppose you have designed some component or die. If you have designed some component in die and go for the simulation or analysis, then you will get some defects at the early stage. Just to correct those defects, you just need to modify your die or your component as well. But in the traditional approach, most of the people doesn't do the work into the die design. They just follow their experience and previous die design, and just easily design the component and design the molds for that. Uh, when these two comes into the die trials, so in the red line shows that the simulation process, blue line shows the traditional approach. So basically, I have a tool named the Inspire Extrude, so I have just name it as the traditional approach. So basically, this line shows the you are going with the help of the simulation results. These are the blue means the traditional approach. So these two comes under the die trial. So experienced guy did not work into this die design process, but simulation results with the guy who have a simulation result, he have a lot many work in the die design, and these two comes under this stage. So in the traditional approach, you have to do more modification required into the die trials, because you put the die on the machine, then you realize that there is some defects or error in your component, then again do the modification and again mount the die to the machine, then die trial 2, trial 3, trial 4, and so on going on. But if you have simulated your part at the designing stage, then you don't need to do that, because you have corrected all these things in the designing stage itself. So what type of you can say the what type of defects in the polymer extrusion process you can predict or easily rectify those defects. So first defect, that is the profile distortion. So basically, profile distortion, what is the profile distortion? So most of you know about the extrusion process, so I just tell you the process. Once you apply the pressure on your toothpaste, so toothpaste has the output profile as the circular. Once you apply the pressure, then your paste comes out in the form of a cylinder or in the form of a circular form. So that is the basic fundamental of the extrusion. So here you can see this is my die, and I have a outcome profile just like this, and my molten metal inserted in this die and apply the pressure. Once my polymer get pressurized, and it will come out of this particular shape, then automatically once the polymer comes out of this shape, then it would have automatically this shape, as you can see on the right hand side. So what is the profile distortion? So sometimes you have a very high speed of your extrusion. So due to having a very high speed, one hand is throwing the material very fast and one hand is throwing the material very slow. It depends on the thickness of your component as well. So that is known as the profile distortion. Once the component get out from the extrusion die, then cools for some time, then it will get distorted. So next is the viscoelastic model. Viscoelastic model means a die swell. So what is the die swell? Here you can see this is a perfect cylinder, and after that it gets the more diameter. So what is happening over there? Uh, this arrow shows that the here is the you can I just explain you in this cut section. This is my inlet, my inlet means to say my polymer is getting into the die from this location. This whole region is the my die surface, and this is the exit. My component is going out from this location. So in the die swell, as this arrow shows that my material is into the die, but when it's come into the die surface, then it's try to tense its original shape. Original shape means it expand little more. So due to which sometime it break the barrier of the tolerance as well. Suppose you have a tolerance of plus minus zero point 0.2, so you got the die swell around the 0.5 or 0.3, so your component would be not in the tolerance of the requirement. So your diameter get changed. And next challenge is the co-extrusion. Co-extrusion basically, suppose you are extruding a component. Let's take example of this shape. You are extruding this component. Blue color polymer is polymer A. Pink color polymer is polymer B. These two polymer are both are different. So what type of challenges you face? So first challenge is that these two polymer get mixed to each other at this joining stage, and due to which, due to this mixing, if this type of component used for the aesthetic process, then it would look weird, because your color combination get changed over this location. And polymer viscosity ratio also affects the this defect. So basically, when the polymer A and polymer B merge with each other, that problem known as the viscous encapsulation. So what is the viscous encapsulation? Here you can easily identify that. Blue color is the polymer 1, yellow color is the polymer 2. So in the viscous encapsulation, it get merged with each other. Here you can see dotted line is the middle line, but red color get mixed with the blue color, and that is not required for the finished component. So that is known as the viscous encapsulation in the co-extrusion process. And same type of defects you have to face with the help of the metal extrusion, metal insert. Suppose you have a metal inserts along with the polymer. So sometimes your metal insert get dislocated from its original position, due to which uh, thickness of the polymer get disturbed. One side thickness is get more, and one side thickness get less. So this type of problem you have to face into the co-extrusion with metal insert. So this viscous encapsulation co-extrusion defects, you can easily predict it at the earlier stage, and do some uh, means to say do some particular exercise to stop these. Clamshell, basically clamshell is nothing that suppose you are pushing the polymer into the die. So most of the time what happens that your die gets open due to the applied force. Your die gets open due to the applied force. So once the die gets open, a small wafer associated your polymer component comes out from the opening. So that is known as the clamshell. clamshell happenings into the die expansions. So move towards the metal extrusion process. Metal extrusion process, there are some other defects are there, as you can see. First is the profile distortion. Here you can see the some example of the profile distortion, how the metal extrusion, actual metal extrusion part and the simulated extrusion part. On the left hand side, you can see the analysis results and the physical tested result. This is the example of the thin profile, and on the bottom right, this is a complex hollow profile, and in the analysis result, you have predicted this defect at the earliest stage. So same type of, but you have not done anything to that, but these type of same extrusion process, extrusion components you get during the production. On the right and top, this is the example of the thick profile and correlation with the actual component. And one more yeah, so one more important factor we have to consider during the extrusion of the metal, that is the die stress comparison. On the left hand side, you can see the maximum stress is the 2750. There are 10 billets are 10 billets are there. In the new design, there are more billets are there, but less stress we are getting. So once you get the more stresses to your die, then your die will get in less life. So you have to keep in mind of this type of stresses as well. So that is the contamination. What is the contamination? Suppose you are extruding a material, so some material get remains into the die. Okay, so once you do the first process and some materials remain into die, and you want to produce another metal extrusion, so the previous one get attached with your second extrusion process. So those contamination you have to trim, or you have to uh, break from the finished good part. Basically it increases the cost of your post processing of your finished component. And same, just for the next defect is the same as the co-extrusion process. In the co-extrusion, there were two different polymers. In the poor seam weld, if you are extruding the metal with two or more than two metal, then once you extrude these metals and they doesn't get merged together, so due to that there is some mechanical weakness is there between the merging point, so that known as the poor seam welds of your different components. And after that, once you extrude the metal, so basically what does the extrusion, here is the best example of the extrusion. It compress the grain structures. It compress the grain structure. So once it's compressed the grain structure, it will show during the simulation that how much it has compressed your grain structure. This one, this is the vector form, this is the, just you can check into the color contour. So it is compressing your metal grain structures. And this one is the some, you can check the exit pressure and pressure contours. On the left hand side, it is showing this, the pressure of your exit finish good component, and on the right hand side, it is showing the how much pressure is being applied by the piston to the metal to get extruded. So basically this is the very main factor we have to consider. Because of this factor we need to assign the machine, how much machine ton is required to extrude the particular component. So only this one is the last manufacturing product we have, that is the Inspire mold for the injection molding simulation. And after that I will take your only 5 minutes just to showcase our meshless technology. So in the Inspire mode, that is used for checking the feasibility of the injection molded parts and for designing the component or designing the complete shot for the injection molding. So basically, as I was talking to earlier, these analytical tool uh, used to reduce the defects, reduce the manufacturing costs, optimize the part, and minimize the molding defects, as you can see. So what are the molding defects? We have the part shrinkage. Part shrinkage means to say your part gets shrinkage during the solidification stage. Sink marks, it gets due to the depression on your surface. Air trap, air bubble get entrapped into the component. Weld lines, I just explain you in some next slide what are the weld lines. So basically in the Inspire mode itself, like the Inspire cast, you don't need to switch between the Inspire product and the CAD product. If you want to do the geometry modification, then you can do into the Inspire molds itself. So here you can see these commands would be used for running the analysis. No other commands are there. Uh, Only these commands are there. You have, if you have to check the feasibility and if you have to go for the full process simulation, only these 4 or 5 commands would be used. So what type of physics it is supporting now? So same, it is supporting 4 type of simulation right now. Basically all type of simulation, all four, these fours are the fully simulation package. So first is the filling simulation. In the filling simulation, it is showing you the filling pattern of your molten metal into the cavity. Packing, basically what is the packing means to say when the machine plunger hold the uh, hold the molten metal into the die after the filling. Because if machine screw comes back after the filling, and due to the uh, vacuum created over there, so it sucks back some molten material from the die. So, and one more reason for the packing is that just to compress the uh, molten plastic into the die. So that holding is the packing simulation. In the holding, it will show you the grain structure of your component, how your grain structure is behaving. And next one is the cooling. In the cooling, how your component is cooling and what type of defects you are getting during the cooling, just like the uh, sink marks. And last one is the warpage. Once you eject the component from the mold, and once you eject the component from the mold, then it will get some deformation its shape due to the uneven cooling, you can say. So you can run all these four individually, or you can go for the complete simulation: filling, packing, cooling, and warpage. Complete simulation package means to say detailed simulation. If you are doing a If you have done with your design, if you have done with your die design, and you want to do the detailed simulation before going to the die manufacturing. After that, you can check the transient mold cooling, fiber orientation of your fiber. Semi-crystalline polymers are also supporting. Hot runner systems are also there. You can assign your runner as the hot runner or the cold runner as per your requirement. So, mhm, let's quickly all this. So basically, it is showing the workflow. First, you have to design the process. Design means to say you have only component, and you just need to design the gate, design the cooling channel, design the runners, etc. Now it is showing some example of the designing on the left hand side. After that, it go for the simulation. In the simulation, how your component is filling, what type of defects you are getting, and after doing the manufacturing simulation means to say if you are going for the whole simulation, detailed simulation, filling, solidification, packing, cooling, and warpage, etc. And these are the results. These are the results you can get during the simulation. In the filling process, you would able to get the temperature contour, velocity, pressure, filling time, air entrapment, weld lines. So basically most of the time people only say the velocity, temperature, pressure, filling time, and weld line in the filling results. In the packing results, on the sink mark, density, and temperature, because some burn marks are also there on the aesthetic surface of the component, so just we need to check that. So in the warpage, we check the displacement. Displacement means to say how much your component is getting displaced from its original location. Cooling, temperature variation, how your component is getting cooled, and what is the mold temperature. So basically, these are the predicted manufacturing defect that you can easily predict at the earliest stage during the designing process. First is the sink mark. Sink mark, you can get the depression on your surface. Basically, some depression, these depression are due to the shrinkage. And next is the weld line. Here you can see the small red color lines are there. Basically, when the two uh, molten metal flow going into different direction, and after some time meet at some particular location. Due to the temperature difference on these two front flows, uh, they do not merge properly with each other, due to which there is a line, there is a formation of line over there, but those line are known as the weld line. So it also impact the structural strength of your component as well. And air entrapment, I have already told you, when the present air in the die does not escape from the die, that get entrapped into the plastic. So that is the air entrapment. Warpage, your component get displaced after ejecting the die. So once you done with the you can say the once you done with the once you done with the molding simulation, so suppose you have simulated this mouse panel you have simulated, so and you have also the designed the mouse panel, but in the designed component you doesn't have any manufacturing defect, but you when you simulate this mouse panel, then it it you can say the it filled with some air entrapment, filled with some welded line, it will fill with some warpages. So I want to check my strength of this mouse panel for the simulated component. So once you're done with molding analysis, the result of the molding analysis you can carry forward for the structure analysis. Means to say linear static, if you want to do, or you want to do for the dynamic analysis. Dynamic analysis means to say frequency response function, transient, random response, model analysis. This type of analysis you can do for the molding simulated parts. So you can get the real picture of your component. If you have defects with your component, and with defects, what are my mechanical strength of the component? So all these things you can cover with the these manufacturing processes. So I have covered our all the manufacturing process. So one more magical tool I have, that is the SimSolid. SimSolid is the rapid assembly verification tool. Means to say the, you can say the, there are lot many more design you can explore with the help of the SimSolid, because SimSolid does not require any mesh. In the previous tools I have explained, the inspire form, inspire cast, inspire mode, you don't need to do mesh, but software do in the background. But in SimSolid you don't require the mesh. So now next question comes into the mind, that how the degree of freedom will lock, and the what basically degree of freedom depends on the node of a element. So how you define the degree of freedom? So basically it require only a CAD geometry, that is unsimplified, not simplified CAD geometry, unsimplified. If you have unsimplified geometry, then no problem, bring it to SimSolid, run the simulation. So next question comes, that how degree of freedom works. So basically degree of freedom in the SimSolid associated with its volume, surface, regions, on this topology features. On this topology feature, degree of freedoms are associated. So basically it is the extension of the finite element method without a traditional mesh. And some solution refinement is performed via you can say the non-polynomial functions, and solution adapted it based on relative local energy density changes and the absolute error on the region boundaries. So these are the some capabilities I have mentioned, that eliminate geometry simplification. You don't need to simplify the geometry. So one sir asked me that in the medical line we need to do the simulation. So if you have some very tiny object, very small type of object, then to mesh those components you only require the fine mesh. But if you have a very large object with a tiny mesh, then it will take a more time to get simulated. So to get rid of this problem, you can also go for the meshless technology. So you can easily uh, easily simulate the large assembly and complex assembly. It does not limit the number of your assembly components. You can easily import and simulate the hundreds, thousand, and lakhs of the component at the same time, and you can also get in the result in very quick time. I will show you some example of the results. Basically, here are the difference between the traditional FE and the SimSolid. So here you can see the some solution and geometry cleanup process has been eliminated. Some geometry cleanup, meshing, and solution process has been eliminated in the SimSolid. In the SimSolid, you just need to provide the connection. Connection means to say if two bodies are connected with each other, so what type of connection they have? They have a fixed bond, they have a sliding connection, they have a some tie bond between each other. Then and if whether they are passing some load to each other. So just apply the connection, and load cases, what type of simulation you want to do: linear, static, dynamic, non-linear, fatigue. And after that, it will take very less time to get simulated and post processing. So for doing a same component, you can direct go for the traditional FEA, or you can go for the SimSolid. Then you will realize that in the traditional FEA it will take a lot time, and in the same model it is taking less, very less time. So this is the uh, graphical representation of the comparison between the classic FEM and the SimSolid. If your part, connection, assembly models are increasing, then your FEA time will increasing as well. If you want to simulate the assembly, it has a thousands of part, then it will take more time. First of all, it will take very more time in the geometry cleanup, then connection, then meshing, then solutions. But there is no concept in the SimSolid. If you have many assembly members are there, so you can directly uh, take it into the analytical tool and run the analysis. So there are some supported solution: non-linear buckling, frequency response, weld automation, non-linear separation, bolt tightening, spot weld automation, fatigue analysis. Fatigue analysis recently added to this tool. And here are some you can see here are some examples that we have run our attend. So it is a 70 parts. It took 4 minutes to get completely analysis. It has robotic arm has the 23 part, and it took 0.5 minutes. It has 160 connection. It took 27 minutes. It has a 7,700 parts and took the 30 minutes. In the half an hour, the whole assembly gets simulated and give you the results for the post processing. Basically, this is the example of the wing, aircraft wing. It has a 2100 connection and done with it into the 5 minutes. And this assembly is for the SPM, special purpose machine. It has on around 2500 of parts. So now you can check the time for the solution. And this is the model, this is dynamic, this is the non-linear, this is another model analysis. Model analysis basically used for to predict the resonant frequency of your component. Linear static, linear static. So, and these are the public case studies that are available in the public domain for the SimSolid. So most of our customers are using this, and it is very popular in the market as well for being a meshless technology. And there are some comparison also in the public domain, that what is the result comparison between the meshless technology with the classic FEM. So what are we getting between these two results? So these two difference between these two results are very close to each other. So I think that slide was not with me. So in the next session, I will show you what is the difference between the result difference between the uh, meshless technology and the classic FEM. So uh, this all about from my side. If you have any question, any query, then please ask. And anything you want to see, then you can please tell me.
Dear participants, hello. Dear participants, is there any query? Dear participant, is there any query? Okay, Jimmy ma'am, kindly conclude the session.
Yes, sir. Thank you, sir, Sharad sir, for your for the informative knowledge and the experience you shared while designing. All the participants, if you have any query regarding this, please feel free to ask. Anyone? Okay. Thank you, Sharad sir, for the knowledge and information you shared. Thank you so much.
Thank you, ma'am. Thank you. Thank you. Thank you very much.
Rajendra sir?
Dear participant, the feedback link is in the chat box. Please find and fill the feedback. Thank you, Sharad sir.
Thank you so much, sir. Thank you so much.
Dear participants, we will meet tomorrow at 8:45 a.m. sharp for this session. Tomorrow first session will be taken by Dr. Rajat Agarwal. And please note that Dr. Rajat has given one task to all of you. Please prepare accordingly. Thank you. Participant, if you find the link and filled the feedback, you may leave now.